Now that we have derivative shortcuts in place for both the sine as well as the cosine function, we're going to use a combination of quotient, reciprocal, and Pythagorean identities to come up with derivatives of the other trigonometric functions. For example, if I were interested in a derivative shortcut for the tangent of x, there is a quotient identity that lets me know that that is equal to the sine of x divided by the cosine of x. So if I'm interested in finding the derivative of the tangent of x, I can simply apply the quotient rule to the quotient sine of x divided by cosine of x. So treating cosine of x as our low and sine of x as our high, this is going to be low d high less high d low over the square of what's below. Now the quotient rule doesn't finish the derivative for us, but it does give us more basic derivatives for us to take. So this will be the cosine of x times the derivative of the sine of x, which we now know is the cosine of x, less high. The derivative of the cosine of x is equal to the negative sine of x, and this will all be over the cosine squared of x. Now, simplifying the numerator with a little bit of algebra, this will be the cosine squared of x minus a negative, that'll be plus the sine squared of x. This is, once again, all over the cosine squared of x. Now, there is debate and argument about how exactly to simplify this expression. The general consensus, though, tends to be use the Pythagorean identity on the numerator and call that 1. Then apply a reciprocal identity and refer to this derivative as the secant squared of x. Why exactly we do that becomes a little bit more apparent in future calc classes, but for now, this is something to be known. Next up, I'd like to do the same thing, but this time I'd like to do it for the cotangent of x. The quotient identity for the cotangent says that that's equal to the cosine of x over the sine of x. So if I want the derivative of the cotangent of x, I can apply the quotient rule to this quotient. So once again, this will be low d high less high d low over the square of what's below. Now, quotient rule doesn't finish the derivatives for us, but it does put them into a more basic form where we should be able to evaluate them more easily. So sine of x times derivative of the cosine of x is negative sine of x less cosine of x times the derivative of the sine of x, which is cosine of x, over the sine squared of x. Continuing to simplify this numerator, this will be the negative sine squared of x minus the cosine squared of x all over sine squared of x. Now, once again, there is a little bit of friendly debate as to what to do to simplify this as much as possible. But the general consensus in the math community is factor out a -1 from the numerator to leave us with, once again, our Pythagorean identity. So replace the sine squared of x plus cosine squared of x with 1. -1 times 1 is -1. Once again, like we did before, we'll apply a reciprocal identity and call this the negative cosecant squared of x. This is the derivative of the cotangent of x. Continuing on, we have two more trigonometric functions to introduce. The next one, we'll do the secant of x. Secant of x is equal to, according to the reciprocal identity, 1 over the cosine of x. So technically, if we have access to the chain rule, there's more than one way to do this. What I'd like to do, though, is stick with the quotient rule for the sake of consistency. So the derivative with respect to x of 1 over the cosine of x, this will be equal to low d high less high d low over the square of what's below. Doesn't finish the derivative for us, but gives us easier things to differentiate. So this will be cosine of x times the derivative of 1. 1 is a constant, so that'll be 0. Minus 1 times the derivative of the cosine of x, that'll be negative sine of x. This is all over the cosine squared of x. Simplifying this numerator as much as possible, the first term drops out completely. The second term we have a negative times a negative, that'll be the sine of x over the cosine squared of x. If you're interested in leaving it in that form, there's nothing wrong with that. But there are those who say that we should express this as a product of two trigonometric functions. These would be the two trigonometric functions if you break cosine squared of x into cosine of x times cosine of x. Applying reciprocal and quotient identities, this will be equal to the secant of x times the tangent of x. Once again, it's generally assumed within the mathematical community that this is the best simplified form of that derivative. Finally, the cosecant of x. According to the reciprocal identity, this would be 1 over the sine of x. So differentiating the cosecant of x is like saying, let's differentiate using the quotient rule 1 over the sine of x. According to the quotient rule, that's going to be low d high less high d low over the square of what's below. The quotient rule doesn't finish the derivative for us, but it does give us more basic forms for us to differentiate. So we will have the sine of x times derivative of 1. 1 is a constant. Derivative will be 0. Minus 1 times the derivative of sine of x would be cosine of x, all over the sine squared of x. Simplifying this as much as possible, the first term in the numerator, sine of x times 0, will become 0. That negative sign does stick around though. So this will be the negative cosine of x divided by the sine squared of x. If we do the same sort of trick as what we did with the derivative of the secant, we can call this negative 1 over the sine of x times the cosine of x over the sine of x. Applying reciprocal and quotient identities, this will be the negative cosecant of x times the cotangent of x. And within most mathematical circles, this is generally agreed on the best form for the derivative of the cosecant function. So be sure to commit all of these derivatives to memory, however you need to do so.